And now let us talk about graphs. Okay, so what exactly is a graph? How does it work? And like what purpose does it actually serve? So graph is a non-linear data structure. Okay, it is a non-linear data structure consisting of vertex or nodes and the edges that connect the two vertices. Okay, I mean vertex or vertices, however you pronounce. A graph can either be directed, like edges have a direction, or be undirected, means edges have no direction. So we provide two implementations. Unweighted graph means the basic graph implementation without edge weights. Okay, I will tell you what those weights are. And a weighted graph means an extended implementation that supports weighted edges and Dijkstra's algorithm. Alright. So now in order to implement, we will be using an adjacency list, okay, but with different underlying data structures. Means an unweighted graph will be using a map, alright, where it has a key of type T, and in that there will be values that will be a set, okay, that will be used for storing the vertices. And in the weighted graph, we will have a map in which the key of type T will have the value, which will also be a map. In that map, the key is of type T and the values of type number. That will be the weight. Alright. So, and there will be common property is directed, means it can be directed, it can be non-directed. Alright. So anyway, our both implementations will support the directed and undirected. So let's first go with the unweighted graph. Alright. The unweighted graph. I will be creating a new folder and unweighted graph.ts, and I'll create class. Class unweighted graph. Here, private vertices map t set t. Alright, this will be our vertices, and private is directed boolean. Okay, now constructor is directed, by default it is false. Vertices equals to an empty map, and this dot is directed equals to is directed. Okay, like this. Now we have a method called as adding a vertex. Add vertex, and will return nothing. So if we do not have that vertex, then this dot vertices dot set vertex new set. Okay, like this. Otherwise it will not set. So we can like basically else it already exists. Now we want to add an edge. Source T and destination T void. Alright, so if the vertex does not exist, then first we will need to add the vertex. Okay. So basically we are adding the edges, those values that will be there inside your set. So now we are going to add edge. So here this dot vertices dot get source dot add destination. So we added the destination to our source, and if it is directed, I mean if it is not directed, then what we do, then we also add the source to the destination. Currently we added destination to the source, now we added the source to destination. Like this. This is how you add an edge. Alright. Now let's talk about removing a vertex. So for visualization, when we will be logging this, you will be understanding more clearly. Okay. Vertex type T, and this will return absolutely nothing. So if there is no vertex for the provided data, then return. Otherwise, for const vertex edges of vertex that we currently have, edge.delete vertex. Okay, so since we are not using this, we can do it like this. And so currently we deleted all the edges pointing to this vertex. Now remove the vertex itself. Like this. Okay, this is how you remove the vertex. Now remove edge. If there is no source or no destination, then return get source, delete destination, and if it is not directed, then dot get destination and delete source, like this. Okay, this is the remove edge functionality. So first get the source and delete the destination from it, and then you get the destination and delete the source from it. You remove the complete connection. That is how you remove an edge. Okay, now we need to get all the vertex. So return array dot from keys. Alright, like this. This will create an array of these keys and get all edges. This will be basically a two-dimensional array, and const edges equals to this, and currently an empty array, and for const vertex and its neighbors, okay, of vertex that we currently have. Now for const neighbor of neighbors, okay. If it is directed or vertex is less than neighbor, edges dot push neighbor. Okay, sorry, like this. Okay. Now return edges. Okay, so only if it is directed, we are, like only if it is directed, or if we find any vertex that whose value is less than the value of the neighbor, means we have found a connection, a connecting edge, and that edge we are pushing into our array. Okay, that connection we are pushing basically. Now get neighbors of a vertex. What we will do is return this dot vertex dot has vertex, then array dot from this dot vertex dot get vertex. Otherwise we will return an empty array. So if it has the vertex, then we'll create an array out of it, then return. Okay, so whatever value that vertex has, basically that only we call the neighbors of it. Okay, now it has a vertex, t boolean this dot vertex dot has vertex, like this. And if it has an edge, then we check that as well. So if it has the source, and if the source has that destination, means we have found an edge. Okay, now we will be having an important method called as the BFS, means the breadth first search. Okay, start start will basically be the vertex. Okay, and this will return an array of type t. So if it doesn't have that vertex, return an empty array. That's it. New set like this, and we will basically have to keep track of what all we have visited, and we do not want the duplicate entries here. That's why. Now the result that we are actually going to push like this, and q. Alright, now while the q has the vertex, we shift it. Okay, so we remove the element from the queue. Now we have that current vertex, and then we push it into the result. Now we check all the neighbors basically. If we haven't visited the neighbor yet, we need to, if the visited still does not contain the neighbor that we are going to visit, so we add that, and we push the neighbor as well, so that we will be checking onto that as well. Alright, so that is how you are going to do the breadth first search. You will be going first to the vertex and then each of its neighbor, and then you return the result. Alright. Now we will do DFS, means depth first search. If vertex does not have this start, then return this empty array. Okay. Now const visited. Now I will take these two things. Okay. Now we will have recursion. Helper function so since we have already visited this, we add it to the visited array. In the result array as well, since we found the vertex, so we search that, and again for const neighbor of this vertex, if we still haven't visited, then need to do all the operations on that neighbor now. Okay, so we will check if that neighbor is vertex inside all the vertex in our graph, and then we will be doing all these operations to it. Helper start return result. Alright. So this way we do. Now the depth first search, search like the depth first. You got the vertex, you did not need a queue this time, you are not searching horizontally. So you got all the neighbor. Now you search on that neighbor. Okay, again you got the neighbor. If it is still not visited, again you search on that neighbor. That is how you implement the DFS. Alright. Now some easy methods like get vertex count number. So let c equals to 0 for const edges of vertex values, and so here oh wait, actually I did not need to do that. Basically, instead of making it complex, just to return this vertex dot size. Oh, sorry. And now get edge count number. Here we will need to implement some logic. So for const edges of text values, all the edges, c plus equals to edges dot size. Okay, return if it is directed, then we will return the count, otherwise count by 2. Okay, sorry, c by 2, like this. That is how you will do, because if it is like not directed, then you do not need to double count it. Now clear means that this dot vertices dot clear. That is how you clear. I mean, these are the methods that the map already has. So this is it in the implementation of the unweighted graph. But now the story is not over, because we are not we have not tested. So now we are going to test. Const graph equals to, or let's say graph, since it is unweighted graph. So new unweighted graph number n graph dot add edge 1 2. So the 1 is related to 2, and this 2 3, like 3 1. Okay, so graph dot get vertices. Alright, you get all the vertices, or like graph dot get edges. Alright, like this. And graph dot bfs starting from 1, and graph dot dfs starting from 3, maybe, or 2. Okay, let me run that code. Okay, look at that. We have these edges 1 2, 1 3, and 2 3. Okay, this is the connection 1 2 3 1, right? Means 1 2, means 1 3, right? And then came back to 1 in the BFS, and this DFS 2 1 and 3. Okay, like this. That is how we did the DFS. Alright, so wait, I think here is some mistake, because we have added the edge 1 2 2 3 and 3 1, and here we like BFS. Okay, 1 check. Let's check our BFS function again. Okay, so here, okay, visited dot push dot shift. Okay, and neighbor on this we haven't visited of that queue.push. Yeah, that is the thing, and we okay. We have this add edge function. All right, so okay. Hmm. Ah, see here visited not add. I need to add that actually. I needed to add that. But anyway, this thing and like pretty much now should be good. 1 2 3 2 1 3, right? So yeah, this thing is done. Wanted to do okay. Let's just verify if our get edges function is also good. Hmm. Yeah, it looks good to me. Okay, so it's pretty much fine here. All right. This is it in the implementation of this unweighted graph. All right. Yeah, so we fixed that issue as well. And now what we will do is that we will be moving on to the weighted graph.